Hello students and welcome to a new lecture. In this lecture we will be talking about the properties of liquids, and we're going to start with the first property that dependent on intermolecular forces, which is surface tension. The surface tension is the resistance of a liquid to spread out and increase its surface area. So think about how water drops like to be in sphere rather than spreading on the surface. They resist the spread, right? And they want to get close to each other, and this is why they end up making spheres rather than spreading on a surface. The stronger the intermolecular force, the higher the surface tension. No wonder water is always going to be spheres, right? Because they have hydrogen bonding. Hydrogen bonding is a very strong intermolecular force. So here is a picture that shows you also like why an insect can actually looks like it can walk on the surface of the water, because it's very light in mass, right? So this is just to show you how the surface of the water they are like holding the molecules. Just think of them holding each other so strongly by intermolecular forces, by that surface tension, that it's hard for a small little light insect like that to break that surface. So it looks like as if the water has like a mirror surface. There is also the capillary action that can be explained by two different ways of molecules interaction when it comes to intermolecular forces. The first one is cohesion. Cohesion are the intermolecular forces that are causing attraction between like molecules, like water to water, alcohol to alcohol, ether to ether, sugar to sugar. Adhesion, on the other hand, is an attraction between two unlike molecules like water and glass, and so on. Here is a couple of pictures that can show us what happens when adhesion and cohesion compete with each other. When we look at water, we always tell you to read the volume of a graduated cylinder, for example. Try to look at the bottom of the meniscus. So what we are trying to say here, that the water surface is going to look like that, right? And the reason for that, think of the water surface as there are the water molecules that's going to attract each other, right? And there are also the glass molecules that are the lining of the graduated cylinder. Now, when it comes to the molecule on the edge, like this one here, right? This water molecule is attracted to its water molecule next to it by cohesion, and the other glass molecule on its left by adhesion. What happens, adhesion is stronger than cohesion, so this attraction is stronger. So therefore, the water molecules try to increase their interaction with the glass, and more of them go up to interact with the glass, right? And this is a scenario where the adhesion with the glass was stronger than cohesion. This is, on the other hand, is Mercury, and the Mercury surface looks the opposite. The concave looks the absolute opposite of water, right? Because again, one more time, the Mercury molecules, let me redraw this again. The Mercury molecules can attract each other via cohesion, but there is the glass molecules here, right? And those glass molecules can also attract the mercury. So if we look at this mercury particle here at the edge, it is definitely trying to avoid contact with the glass and go stronger with the other mercury. And that's why the concave is the opposite shape of water, because in this case, cohesion is stronger than adhesion. All right. Now, another property that dependent on intermolecular forces is viscosity. Viscosity is the measure of a fluid's resistance to flow. an example, like when you pour water, it's a very different way or feeling for the liquid than when you pour honey. Honey or heavy or thick oil seems to have more resistance to flow and more viscous. So also there is like it is the measure of a fluid resistance to flow. If you drop a metal sphere in two different liquid, if it goes down very fast, like in the case on the right, it means that the liquid was not viscous. But if there is a resistance for the flow, then it's going to take a while for that sphere to drop at the bottom. So this is also dependent on intermolecular forces. The stronger the intermolecular forces, the higher the viscosity. So the viscosity then is a measure of intermolecular forces. If I'm asking you which of the following liquid is supposed or projected to be more viscous, you really need to analyze what kind of intermolecular forces we're looking at. Now that also leads us now to think of water and why water is a very unique substance. Water is the only matter in which the solid state is less dense than the liquid state. And the reason for that, it's when you bring the temperature down, you allow those molecules to spread, and when they do so, they maximize the amount of intermolecular forces between them. And that kind of looks something like that. So if I have a water molecule here and I slow it down in a solid state, every water molecule right now will take its sweet time to hydrogen bond to another water molecule, right? And because they are not moving fast right now, I cool them down, they actually can do so. While in liquid, they move too fast, so they don't allow for this separation. Now that big separation will make less molecules per volume, which is the density is mass over volume, right? That's what density is. So that means that I will have less mass in a volume, and that's why ice is less dense than liquid water. And that gives water special property to make it the molecule of life, because imagine if lakes will freeze from the bottom up, then that will kill the whole marine life, which will affect the whole life cycles and food cycles, which will ruin life pretty much on Earth. As you can tell, the density of the water does decrease with does have the highest amount comes around 4 degrees Celsius, but you can see here that when you go to the solid, which is lower than the 0 degree here, that the solid here is lower than the highest of the liquid, which is 4 degrees Celsius and higher. This is when you have a liquid higher density than ice. All right, I will see you in the next lecture. I hope you enjoyed this lecture. Thank you.